there is a wall at the edge of everything. Not a metaphor, not a philosophical concept invented to comfort the frightened. A real physical boundary, one that light itself cannot cross. One that your mind, no matter how trained or disciplined, will shatter against the moment it tries to see past it. The universe ends, and what waits on the other side will not let you sleep tonight. Let that land for a moment, not the poetic version of it. The true, scientific, documented, peer-reviewed version. The universe, every star you've ever seen, every galaxy captured by every telescope ever built, every photon that has traveled since the first second of existence. All of it fits inside a boundary, a horizon, a place where space itself stops being the space we understand and becomes something else entirely. Something we do not have a word for. Something we are only beginning to measure. This is not the end of human imagination. This is the end of the observable cosmos. And beyond that edge, the physics we know begins to unravel like a thread pulled from a sweater in the dark. Consider what you know about distance. The closest star to Earth, outside our own sun, is Proxima Centauri, 4 light-years away. That means light, traveling at 300,000 kilometers per second, takes 4 full years just to reach us from our nearest neighbor. The Milky Way, our home galaxy, the only cosmic address we have ever known, stretches 100,000 light-years from edge to edge. 100,000 years of uninterrupted light-speed travel just to cross the place we call home. And then beyond our galaxy, there are 2 trillion more. 2 trillion galaxies, each one containing hundreds of billions of stars, each star potentially orbited by worlds. The numbers are so large they stop functioning as numbers. They become abstract weights, burdens too heavy for the human nervous system to actually carry. And all of it, every single one of those 2 trillion galaxies, fits inside the observable universe, a sphere approximately 93 billion light-years in diameter. That is the edge. That is the wall. But here is what they don't tell you in school textbooks. Here is where the real terror begins. That wall is not where the universe ends. That wall is only the limit of what we can see. A horizon created not by the edge of matter, but by the speed of light and the age of time itself. Light from beyond that point has simply not had enough time to reach us yet, because the universe has only existed for 13.8 billion years. The universe itself, the full, actual, total universe, is almost certainly vastly larger. Some models suggest it is at least 250 times larger than what we observe. Other models, grounded in the mathematics of cosmic inflation, the violent expansion that occurred in the universe's first fractions of a second, suggest the full universe is so much larger than what we can see that the observable universe, our entire 93 billion light-year bubble, is nothing more than a single grain of sand on an infinite beach. Infinite. That word. Feel its weight. Not very large. Not immeasurably big. Infinite. Without end. Without boundary. Without a wall on the other side. And if the universe is truly infinite, then everything that can happen does happen. Somewhere. Every configuration of matter and energy that obeys the laws of physics plays out in full in some distant region of the cosmos we will never reach. That means there are other versions of this exact moment happening right now as these words enter your mind, in regions of space so remote they are functionally in a separate universe. Copies of Earth, copies of you, Every decision you did not make, made. Every path you did not take, taken. This is not science fiction. This is a direct mathematical consequence of an infinite universe. And the mathematics behind it is the same mathematics that correctly predicted the cosmic microwave background radiation, the large-scale structure of galactic filaments, and the accelerating expansion of space that astronomers confirmed in 1998 and that earned a Nobel Prize in 2011. The universe has an end. At least, the universe we can observe does. And what sits beyond that edge is either an infinite ocean of space and matter, and alternate realities extending forever in every direction, or something even stranger. Something that might not be space at all. Because there is another answer to the question of what lies beyond the observable horizon. An answer that comes not from telescope data or redshift measurements, but from the deepest layers of theoretical physics. An answer that suggests the universe, at its largest scales, may not be a single continuous thing, but one bubble in a churning, eternal ocean of other bubbles, other universes. Each one born from a quantum fluctuation, each one governed by its own laws of physics, its own constants, its own version of reality, some of them warm and bright and full of stars, and some of them cold and structureless and dark from their very first moment of existence. The multiverse. And it is not a fantasy. It is the most mathematically consistent solution to some of the deepest problems in modern physics. We are standing at the edge of everything we know. And something is standing on the other side. The universe is not static. It never was. Even in the moments when ancient civilizations looked up at the night sky and saw permanence, a fixed dome of stars, an eternal canopy stitched with light. The cosmos was already in violent, relentless motion, expanding, stretching, pulling itself apart at speeds that defy every intuition the human mind was built to hold. In 1929, Edwin Hubble confirmed something that shook the foundations of physics. The galaxies are moving away from us, every single one of them. And the farther away a galaxy sits, the faster it recedes. Not because the galaxies themselves are flying through space like scattered shrapnel from some ancient explosion, but because space itself is expanding. The fabric of reality is stretching, and the galaxies are simply riding that stretch, carried apart like dots painted on the surface of an inflating balloon. This was already strange enough. Then came 1998. Two independent teams of astronomers studying a specific type of exploding star called a Type Ia supernova, a stellar detonation so consistent and predictable that cosmologists use it as a measuring stick across cosmic distances, expected to find that the expansion of the universe was slowing down. Gravity, they reasoned, should be pulling everything back toward everything else. The expansion should be decelerating. It should eventually stop. Instead, they found the opposite. The expansion of the universe is accelerating. Space is not just growing, it is growing faster every second. The galaxies are not coasting, they are being pushed. Something invisible, something that carries no mass and emits no light, and interacts with nothing we can measure directly, is woven into the very fabric of space-time and is actively driving the universe apart with increasing force. They called it dark energy, and here is where the architecture of the end begins to reveal itself. Because dark energy does not simply make the universe large. It makes the universe lethal. It encodes into the deepest structure of reality an inevitable and irreversible fate. A fate so total, so absolute, so final, that it makes every human concept of ending, death, extinction, the heat death of civilizations, look like a brief nap before the real darkness begins. Think of it this way. Imagine you are standing in the center of an enormous field, and in every direction, you can see other people scattered across the landscape. At first, they are far away, but visible, small figures on the horizon. Now imagine the field itself begins to grow. The ground stretches beneath your feet, and those distant figures begin to move away, not because they are walking, but because the ground between you is multiplying. New ground is appearing from nothing, inserting itself between you and every other person in the field. At first, the figures simply become smaller, more distant. Then, at some point, they reach a distance so great that even light cannot cross the gap fast enough to reach you anymore. And then, one by one, they vanish. Not because they have died, not because they have been destroyed, but because the space between you has grown so vast that they have crossed beyond your horizon. They are gone, not from existence, but from your universe, from your reachable, knowable, observable world. This is not a metaphor for loneliness. This is the documented, measured, mathematically certain future of our cosmos. Galaxies are already disappearing over our cosmic horizon. Right now, as you exist in this specific second of this specific century, there are galaxies receding from us faster than the speed of light. Not violating Einstein's laws, because it is not the galaxies moving through space, but space itself expanding beneath them. And those galaxies have already been lost to us forever. No signal we send will ever reach them. No probe, no beam of light, no message in any form will ever bridge that growing void. They are gone, and in approximately 150 billion years, a number so large it erases the current age of the universe the way the ocean erases a sand castle. The Milky Way and its nearest gravitationally bound companions will be the only galaxies left inside our observable horizon. Everything else will have been swallowed by the expanding dark. The night sky, which today contains 2 trillion galaxies, will be almost entirely empty. A civilization alive in that era, if any consciousness survives that long, will look out at a black and featureless void and have no evidence whatsoever that other galaxies ever existed. The cosmic microwave background radiation, the faint glow of the Big Bang that we use today to reconstruct the entire history of the universe, will have been stretched by expansion into wavelengths too long to detect. The fossil light of creation will be gone. They will be alone in a way no living thing in this era can truly comprehend. And the architecture of ending does not stop there. Because after the galaxies vanish, the stars begin to die. Stars are not eternal. They are engines, nuclear furnaces that burn through their fuel on timescales that feel eternal from a human perspective, but are, in the full measure of cosmic time, startlingly brief. The most massive stars, the brilliant blue giants that blaze with the light of millions of suns, last only a few million years before they detonate in supernovae, seeding the surrounding gas clouds with the heavy elements that will eventually become planets, and, on at least one of those planets, biology. Our own sun, a modest, middle-aged yellow star, has approximately 5 billion years of fuel remaining. When it exhausts its hydrogen core, it will expand into a red giant, engulfing Mercury, Venus, and almost certainly Earth, before shedding its outer layers into a glowing planetary nebula and leaving behind a crystalline white dwarf no larger than our planet. A cooling ember that will dim across trillions of years into cold, a dark silence. The last stars, the smallest, most miserly red dwarfs, burning their hydrogen so slowly and carefully they could last 100 trillion years, will eventually exhaust even their patience. And when the last one flickers out, the universe will enter an era that has no analog in any human experience. An era so dark, so cold, and so structureless that the word darkness, as you understand it, does not begin to describe it. This is the era of the black holes, for a period spanning numbers written with more zeros than there are atoms in the observable universe. The cosmos will be dominated by black holes, the collapsed remnants of dead stars, and the supermassive engines that once sat at the hearts of galaxies. They will drift through a universe so cold it approaches absolute zero, slowly absorbing whatever sparse matter remains, growing incrementally larger across timescales that make the current age of the universe look like the first tick of a clock that will run for eternity. And then, even the black holes will die. Stephen Hawking demonstrated through a synthesis of quantum mechanics and general relativity that black holes are not truly permanent. They radiate, slowly, imperceptibly, across unimaginable timescales. Black holes leak energy in the form of what is now called Hawking radiation, a quantum effect at the event horizon, where particle-antiparticle pairs are spontaneously created, one falling in, one escaping, and the black hole losing mass with each interaction. A stellar mass black hole will fully evaporate in approximately 10 to the power of 67 years. A supermassive black hole, billions of times more massive, will take 10 to the power of 100 years. But it will evaporate, every one of them, until the last black hole releases its final quantum of radiation into a universe that is cold beyond description, dark beyond measure, and expanding still, forever, into a void so complete that even the concept of emptiness will seem, by comparison, crowded. This is the heat death, the thermodynamic end state of a universe governed by the second law. Entropy always increases, order always dissolves, energy always spreads until no gradient remains to drive any process, any reaction, any thought. But here is the question that lives on the far side of that ending. The question that the architecture of cosmic death does not answer, cannot answer, and perhaps was never designed to answer. What happens to the laws of physics when there is nothing left to govern? The laws of physics are not the universe. This distinction sounds simple. It sounds almost obvious. But sit with it for a moment. Really sit with it. Because embedded inside that single sentence is one of the most disorienting ideas in the history of human thought. The laws of physics are descriptions. They are the rules we have extracted from observation, from experiment, from the painstaking accumulation of data across centuries of scientific inquiry. They describe how matter behaves, how energy flows, how space curves in the presence of mass, how time dilates under velocity and gravity. They are extraordinarily precise. They are the most accurate intellectual tools our species has ever constructed. But they are not the thing itself. They are the map, and the universe is the territory. And when the territory ends, when the last black hole exhales its final quantum whisper into an infinite, frozen void, what becomes of the map? Does it dissolve with the territory it described? Or does it persist, somehow, as a ghost of logic floating in a space that no longer contains anything to be logical about? Do the laws of physics exist when there is no physics left to govern? This is not a rhetorical question. It is the doorway through which modern theoretical physics walks every single day. And what waits on the other side of that doorway is something that should make every thinking person stop and feel the full weight of their own smallness. Consider the quantum vacuum. In the deepest understanding of quantum field theory, the framework that describes the behavior of every particle and force we have ever detected, empty space is not actually empty. The vacuum is not nothing. It is a seething, invisible ocean of quantum fluctuations, a constant boiling of virtual particles that pop into existence and annihilate each other so rapidly they cannot be directly observed, but whose effects are measurable, documented, and real. The Casimir effect, a tiny but verified attractive force between two uncharged metal plates placed nanometers apart, is a direct physical consequence of the quantum vacuum. Empty space pushes. Empty space has energy. Empty space is not the absence of everything. It is the presence of something we do not yet fully understand. And this matters enormously for the question of what exists beyond the end. Because if the quantum vacuum persists even after all matter, all energy, all radiation has been stretched to irrelevance by the expanding cosmos. If the vacuum state of space-time itself endures, then the end of the universe is not truly the end of something. It is the persistence of a substrate, a ground state. A silent, frozen ocean of quantum possibility with nothing on its surface and nothing in its depths, but an ocean nonetheless. And oceans, given enough time, produce waves. Here is where the physics becomes genuinely staggering. In a universe governed by quantum mechanics, a state of perfect, permanent stillness is forbidden. The Heisenberg uncertainty principle, one of the foundational, non-negotiable features of reality at the quantum scale, dictates that no system can simultaneously have a perfectly defined energy and a perfectly defined state across time. There will always be fluctuation. There will always be uncertainty. There will always be a non-zero probability of change, of deviation, of spontaneous departure from the equilibrium. Even in the maximum entropy state of a dead universe, something can happen. The probability is vanishingly small. The timescale required is so astronomically large, it cannot be expressed in any notation that feels meaningful. But in an eternal universe, or even a universe that simply persists long enough, a timescale that is merely very, very, very large is not the same as infinite. And across a timescale that is not infinite, a probability that is not zero will eventually resolve. This brings us to one of the most haunting concepts in all of theoretical physics: the Boltzmann brain. Ludwig Boltzmann was a 19th century Austrian physicist whose work on statistical mechanics and thermodynamics laid the groundwork for our modern understanding of entropy. He understood, with devastating clarity, that the second law of thermodynamics is not absolute in the philosophical sense. It is statistical. Entropy increases not because the universe is compelled to disorder by some cosmic mandate, but because there are so many more ways for a system to be disordered than ordered that disorder is simply overwhelmingly probable. Order is rare. Complexity is rare. Life is astonishingly, almost impossibly rare. But rare is not the same as impossible. And here is where Boltzmann's logic leads to a conclusion so strange it feels like a fever dream disguised as mathematics. In a universe that persists long enough, across timescales measured in numbers that require exponential notation stacked upon exponential notation, random quantum and thermal fluctuations will, purely by chance, occasionally produce ordered structures. Small ones first. A molecule appearing from nothing. Then a crystal. Then, given incomprehensible spans of time, structures of arbitrary complexity, and eventually, so rarely that the word eventually barely survives the journey, a fluctuation large enough to spontaneously produce a fully formed, conscious mind. A brain, complete with false memories of a life never lived, sensory experiences of a world that does not exist, a sense of self coherent enough to think and feel and wonder where it came from. A Boltzmann brain, appearing from the thermal noise of a dead universe, existing for a fraction of a second before dissolving back into entropy, never knowing what it was, never knowing it was alone. This is not science fiction. This is the direct logical consequence of combining the laws of statistical thermodynamics with the infinite time implied by an eternally expanding universe. Physicists take it seriously, not because they believe it is common, but because they cannot make it impossible. And a consequence that cannot be made impossible, given infinite time, becomes inevitable. But this raises a question that cuts far deeper than cosmology. How do you know you are not one? How do you know that the memories you carry, the life you believe you have lived, the world you believe surrounds you, the people you believe you have loved, are not the spontaneous constructions of a quantum fluctuation that assembled your consciousness in the last fraction of a second, complete with every false impression of continuity and history? You cannot, not with certainty. The same laws of physics that describe your existence in a structured 4-billion-year-old biosphere on an ancient rocky planet also permit, in principle, your existence as a momentary ghost of order in an otherwise dead cosmos. This is the philosophical abyss that opens when you follow the science honestly all the way to its edge. And standing at that edge, looking down, the question of what exists beyond the observable universe begins to feel less like a question about astronomy and more like a question about the nature of reality itself, about whether the universe is a container for experience, or whether experience is something that leaks out of the universe under the right conditions, assembling itself from noise, from nothing, from the quantum basement of a cosmos that no longer contains a single star. There is another possibility, though, one that does not require waiting for Boltzmann's impossible lottery to pay out, one that emerges not from thermodynamics, but from the mathematics of the very beginning, from the theory of cosmic inflation and what it implies about the structure of everything that exists. It suggests that our universe did not begin from nothing. It suggests that our universe was born, that the Big Bang was not the creation of existence, but a transition, a phase change, a moment when a region of a pre-existing, eternal, frothing quantum substrate crossed a threshold and converted its energy into the hot, dense, expanding space-time we call home. And that same process, the same quantum mechanism that created everything we have ever known, is happening constantly in other regions, producing other universes, other space-times, other sets of physical laws, other forms of existence we have no language to describe. The void beyond our horizon is not empty. It is a womb. There is a number that haunts modern physics. It is not a large number. It is not dramatic in appearance. It sits quietly in the equations that describe the fundamental forces of nature. A small decimal, a ratio, a constant so precise and so specific that if it were even fractionally different, not a single atom in the observable universe would exist. Not a star, not a planet, not a molecule of water, not a single moment of biology anywhere across the 14 billion years of cosmic history. That number is the fine structure constant, approximately 1 divided by 137. It governs the strength of the electromagnetic force, the force that holds electrons in orbit around nuclei, that makes chemistry possible, that allows light to interact with matter, that underpins every biological process that has ever occurred on this planet. And it is precisely, inexplicably, perfectly calibrated to allow complexity to exist. Change it by a few percent in either direction, not dramatically, not drastically, just slightly, and atoms become impossible. Chemistry vanishes. Stars cannot form stable cores. The universe becomes a place of pure, structureless radiation, expanding forever into darkness without ever producing anything capable of noticing the darkness. This is called the fine-tuning problem, and it is not limited to the fine structure constant. There are at least 26 fundamental constants in the standard model of particle physics. Numbers that describe the masses of particles, the strengths of forces, the ratios between fundamental quantities. And every one of them appears to be calibrated within extraordinarily narrow ranges that permit the existence of complex matter. The cosmological constant, which describes the energy density of the vacuum, the dark energy that drives the accelerating expansion of the universe, is tuned to a precision of 1 part in 10 to the power of 120. That is not a typo. 1 followed by 120 zeros in the denominator. The most precise calibration of any quantity in all of known physics, pointing at a value that allows galaxies to form without being immediately shredded by runaway expansion. The question that hangs over all of this, the question that physicists and philosophers have wrestled with for decades, is devastatingly simple. Why these numbers? There are 3 possible answers. The first is that the constants are not truly fundamental, that some deeper, undiscovered theory will eventually explain why they must be exactly what they are. The way Einstein's general relativity explained why Newton's gravitational constant takes the value it does. This is the hope of the theorists who believe in a final, complete description of nature. A theory of everything, a single equation from which all of reality's constants emerge as necessary consequences rather than arbitrary choices. The second answer is that the constants were chosen, that behind the mathematical structure of the universe, there is an intelligence, a designer, a will that set the dials with intent. This answer lives in theology, not physics. But the precision of the tuning is so extraordinary that even physicists who find the theological answer deeply uncomfortable are forced to acknowledge why so many people find it compelling. The third answer is the one that modern cosmology, pushed by the mathematics of eternal inflation, keeps arriving at despite the philosophical discomfort it produces. There is no single set of constants. Every possible combination of fundamental constants exists somewhere. In some universe within an eternal, self-reproducing multiverse, the fine structure constant is twice what it is here. In another, it is half. In another, the cosmological constant is 1,000 times larger. And that universe expanded so rapidly after its birth that no galaxy ever had time to coalesce from the primordial fog. In another, the strong nuclear force is slightly weaker, and protons decay before hydrogen atoms can form stable structures. Universe after universe after universe. Each one a different roll of the quantum dice, each one governed by its own unique physical law, most of them dark and sterile and structureless, and a vanishingly small fraction of them, by pure probability, happening to land on the extraordinary, improbable combination of constants that permits stars, chemistry, biology, and consciousness. We exist in one of the lucky ones. Not because it was designed for us, not because we are special in any cosmic sense, but because in an infinite multiverse of possibilities, all possibilities are realized. And only in the universes where the constants permit observers to exist will there be observers to notice the constants. This is the anthropic principle, stated without comfort or consolation. We find ourselves in a universe compatible with our existence because we could not possibly find ourselves in any other kind. This is logically airtight. It is also existentially vertiginous because it means that everything we have ever called a law of nature, every principle we have treated as a deep, necessary truth about reality, may be nothing more than a local ordinance, a regional regulation that applies only within our cosmic bubble, as arbitrary and contingent as the particular geography of a country's borders. The speed of light, the mass of the electron, the strength of gravity. Not eternal truths carved into the bedrock of existence, but the specific outcome of a quantum fluctuation that happened to nucleate our particular bubble of space-time with these particular parameters. In the next bubble over, the laws are different, and in that universe, if there is any form of mind capable of reflection, it looks out at its own cosmos and calls its own constants the laws of nature, never knowing that an infinite landscape of other possibilities surrounds it on all sides, forever beyond reach, forever beyond proof. This is the landscape, the term physicists actually use for the vast space of possible physical laws implied by string theory and eternal inflation. A landscape of perhaps 10 to the power of 500 distinct vacuum states, each one corresponding to a different universe with different constants, different particles, different forces. 10 to the power of 500 is not a number that can be visualized. It is not a number that can be felt. It is a number so large that if you devoted every atom in the observable universe to writing its digits, you would run out of atoms before you ran out of number. And each one of those vacuum states may be a real, existing universe. This is where the ground beneath every human certainty begins to soften. Because if the laws of physics are not universal, if they are local, contingent, variable across the landscape of an eternal multiverse, then the entire project of physics as a search for final, necessary truth becomes something more complicated, something more humble. We are not uncovering the deep structure of all possible existence. We are mapping the specific, improbable, locally valid rules of our own cosmic neighborhood. We are not reading the book of nature. We are reading one page from a library so vast it contains every possible book, including every possible version of itself, including versions written in languages that have no analog in any human tongue. And yet, and this is the fact that should arrest every impulse toward nihilism, within this page, the words are coherent. The mathematics works. The equations describe. The predictions match the measurements to dozens of decimal places. Whatever our universe is, however contingent, however local, however improbable, it is structured. It is consistent. It is, in the deepest sense, intelligible. The universe did not have to be intelligible. In most regions of the multiverse, if the landscape is real, the local laws produce nothing capable of understanding them. Sterile bubbles of space-time expanding forever in the dark, their mathematics unread, their constants uncelebrated. And yet here, in this specific, improbable, fine-tuned pocket of the eternal foam, matter organized itself across 4 billion years into structures capable of asking why the fine structure constant is 1 divided by 137. That is not nothing. That is, perhaps, the most extraordinary fact in the history of facts. That the universe, in at least one of its iterations, became aware of itself. That the void learned to wonder about the void. That the mathematics of existence produced from within its own machinery a mind capable of reading the mathematics. And that mind is now standing at the edge of everything it knows. Looking outward into a landscape it may never fully see. Asking questions the universe may not be built to answer. Time had a beginning, not in the poetic sense, not as a narrative device to frame the drama of cosmic history. In the precise, technical, mathematically rigorous sense, time itself. The dimension along which every event unfolds, every cause precedes every effect, every living thing ages and eventually stills, did not always exist. There was a moment before which the word before has no meaning. A threshold below which the concept of sequence dissolves entirely, not because our instruments are too crude to measure it, but because the structure of space-time itself breaks down at that boundary, and the question of what came before becomes, in the strictest physical sense, grammatically malformed, like asking what lies south of the South Pole. The question sounds valid. It follows the rules of language, but it points at nothing. Because the coordinate system that gives the question meaning ceases to exist at the very point the question addresses. This is what physicists mean when they say the Big Bang was the beginning of time. And it is one of the most disorienting facts in the entire architecture of human knowledge. Because the human mind is a machine built for sequence. Every thought you have ever had unfolds along a timeline. Every memory you carry is stamped with a sense of before and after. Every plan you make assumes a future that has not yet arrived. Causality, the principle that effects follow causes, that nothing happens without something making it happen, is so deeply embedded in the way consciousness works that to imagine its absence is not merely difficult. It is, in the most literal sense, unthinkable. The mind reaches for it and finds no surface to grip. And yet the physics is unambiguous. At the Planck time, 10 to the negative 43 seconds after the nominal 0 point of the Big Bang, the smallest interval of time that current physics can meaningfully describe, the universe was so hot, so dense, so compact that quantum gravitational effects dominated everything. General relativity, which describes the large-scale curvature of space-time, breaks down completely at this scale. Quantum mechanics, which governs the behavior of matter and energy at the smallest scales, also breaks down. The two theories that together account for essentially every physical phenomenon we have ever observed become mutually incoherent in the first Planck moment of existence, producing infinities where equations should produce numbers, and silence where physics should produce answers. We do not know what happened at the beginning, not in the sense of lacking data, in the sense that the theoretical framework required to describe that moment does not yet exist. The physics of the Planck era requires a complete theory of quantum gravity, a synthesis of general relativity and quantum mechanics that has been the central unsolved problem of theoretical physics for nearly a century. String theory attempts it. Loop quantum cosmology attempts it. Causal dynamical triangulation attempts it. Each framework produces partial insights and deep mathematical beauty, and none of them produces a complete, testable, universally accepted description of what the universe was doing in its first Planck moment. The beginning of time is, quite literally, the edge of what physics can currently see. But here is where it becomes truly strange. Here is where the science stops being merely humbling and starts being something closer to metaphysically vertiginous. Loop quantum cosmology, one of the most mathematically sophisticated approaches to quantum gravity, suggests that the Big Bang was not a true beginning. That when the equations of quantum geometry are applied to the collapsing geometry of a pre-existing universe, the singularity that general relativity predicts, the point of infinite density and zero volume where physics breaks down, does not actually occur. Instead, quantum effects generate a repulsive force at extreme densities, a kind of cosmic pressure that halts the collapse before it reaches the singularity and bounces the universe outward into a new expansion. A big bounce. Our universe, in this framework, did not emerge from nothing. It emerged from the compression of a previous universe. A cosmos that expanded, reached its maximum extent, began to contract under its own gravity, collapsed inward across billions of years, and then, at the moment of maximum compression, rather than reaching a singularity, rebounded. The Big Bang that we treat as the absolute beginning of everything may be the echo of a previous universe's death. A phoenix transition, a cycle of cosmic death and rebirth that has no beginning in the same way a circle has no beginning. A sequence of universes, each one born from the collapse of its predecessor, stretching backward through time in an infinite regression that makes the question of what came before our universe as answerable and as unanswerable as the question of what integer comes before the infinite sequence of negative numbers. There may always have been something, and this collides head-on with one of the deepest intuitions of human philosophy. The intuition that nothing is simpler than something, that the default state of existence is absence, and that the existence of anything at all requires an explanation that points beyond itself. Leibniz asked it centuries ago, and the question has never been more urgent. Why is there something rather than nothing? The physicist's answer, emerging from quantum cosmology, is increasingly radical. Nothing, in the quantum sense, is unstable. A true, absolute, perfect nothing. A state with no space, no time, no energy, no fields, no quantum fluctuations, is not a stable equilibrium. It is, in fact, impossible to maintain, because the very definition of a quantum vacuum includes irreducible fluctuations that cannot be suppressed without violating the uncertainty principle. A perfect nothing would require perfect knowledge of both energy and time simultaneously, and that is precisely what quantum mechanics forbids. Nothing, therefore, cannot last. Given the laws of quantum mechanics, or perhaps more accurately, given any laws even remotely resembling the laws of quantum mechanics, a state of absolute nothingness is intrinsically prone to spontaneous transition into a state of something. The universe did not emerge from nothing despite the laws of physics. It emerged from nothing because of them. But this raises the question that stands at the very back of the room, the question that has been waiting patiently since the first word of this journey. The question that all the cosmology and quantum mechanics and inflationary theory has been circling without quite reaching. Where did the laws come from? Not the constants. We have seen how those might vary across the multiverse. The laws themselves. The principle that quantum fluctuations occur. The principle that energy is conserved. The principle that causes precede effects. That mathematics describes physical reality with unreasonable precision. That the universe is structured in a way that minds can read. These are not constants that vary across the landscape. These are the rules of the landscape itself. The grammar of the book, not the words on the page. And there is no physics that explains them. There cannot be. Because any physical explanation would itself rely on laws, and the question of where those laws come from simply re-emerges one level deeper. It is turtles all the way down, except that at some point the turtles run out and you are left standing on nothing, looking down into an absence so complete that even the concept of explanation loses its footing. Roger Penrose proposed a framework called conformal cyclic cosmology, a model in which the universe cycles through infinite eons, each one beginning with a big bang and ending in an infinitely expanded, cold, empty future state that is, through the mathematics of conformal geometry, identical in structure to a new Big Bang. The end and the beginning share the same geometry. The death of one universe is the birth of the next, not through collapse, but through a mathematical equivalence between infinite expansion and infinitesimal compression at the level of conformal scale. The end looks exactly like the beginning. The omega and the alpha, the last quantum whisper of a dying universe, stretched across an infinite cold void, geometrically indistinguishable from the first incandescent moment of a new one. The Ouroboros, the ancient symbol of the serpent consuming its own tail, encoded not in mythology, but in the differential equations of space-time geometry. And somewhere inside that cycle, in one of its infinite iterations, a species of primate on a rocky planet orbiting an unremarkable star looked up at the night sky and began to ask questions. Questions the universe may have always been asking itself, through us. We are made of the universe looking at itself, not as poetry, not as consolation, as precise, documentable, physical fact. Every atom of carbon in your body was forged in the nuclear furnace of a star that lived and died before the sun existed. The iron in your blood was produced in the core collapse of a supernova, a stellar explosion so violent it briefly outshines entire galaxies, scattering its newly synthesized heavy elements across light years of interstellar space, seeding the molecular cloud that would eventually collapse under gravity into our solar system. The oxygen you are breathing right now was exhaled by dying stars across billions of years of cosmic history. The calcium in your bones, the phosphorus in your DNA, the sodium that carries electrical signals between your neurons at this exact moment, all of it, every atom, every particle, traces its origin to stellar nucleosynthesis, to the violent, creative death of suns. You are not in the universe. You are the universe, temporarily, improbably, magnificently assembled into a form capable of contemplating its own existence. And that fact, held honestly, without the cushion of familiarity, is one of the most staggering things that has ever been true about anything. Consider the chain of contingency that had to hold for this moment to exist. The Big Bang had to produce a matter-antimatter asymmetry, a tiny, unexplained imbalance of approximately one extra particle of matter for every billion particle-antiparticle pairs. Or everything would have annihilated in the first seconds, and the universe would contain nothing but radiation forever. The fundamental constants had to land within the extraordinarily narrow range that permits atoms, chemistry, and stellar ignition. The Milky Way had to form in a region of the cosmic web stable enough to produce second-generation stars rich in heavy elements. The sun had to form with enough mass to burn stably for billions of years, but not so much mass that it burned out in millions. The Earth had to form at a distance that permits liquid water. The moon had to exist, its gravitational influence stabilizing the axial tilt of Earth within the range that produces consistent seasons rather than wild, sterilizing climate oscillations. And then, Across 4 billion years of chemistry experimenting with itself, life had to begin. Not once, not inevitably, but under specific conditions, in specific chemistry, producing self-replicating molecules that could carry information forward through time. Evolution had to run its blind, patient, ruthless algorithm across billions of generations, producing increasingly complex nervous systems. Until one particular lineage of social primates developed a prefrontal cortex large enough to model not just the immediate environment, but the entire history and future of the cosmos. Every single link in that chain had to hold. And here you are. This is the weight of what you are. Not in the diminishing sense, not the perspective that says you are small, therefore insignificant. In the expanding sense. The sense that says the universe is 13.8 billion years old. And it took every one of those years, every stellar death, every galactic collision, every quantum fluctuation, every cosmic coincidence stacked upon cosmic coincidence to produce this moment of awareness. To produce a mind that can hold the concept of 93 billion light years and feel something in response to it. That response, that feeling, is not a distraction from the science. It is the science's most extraordinary product. But now hold everything we have traveled through in this journey and feel its full combined weight. The observable universe ends at a horizon we cannot cross. Beyond it, space continues, almost certainly infinitely, in a dark ocean of matter and energy we will never reach and never measure. The universe itself is accelerating toward a heat death so total that even the concept of temperature will eventually become meaningless. Because temperature requires a difference in energy between regions, and the final state of maximum entropy is a state of perfect, featureless uniformity. A cosmos in which nothing is hotter than anything else, and therefore nothing can ever happen again. The last black holes will evaporate across timescales written in exponential towers of numbers. The final quantum of Hawking radiation will disperse into an infinite, frozen void. And then there will be, for all practical purposes, nothing. Except that nothing, as we have seen, is unstable. And so, across timescales so vast, they make the current age of the universe look like the first Planck moment after a new Big Bang. The quantum vacuum will fluctuate. Most fluctuations will be infinitesimal. Tiny ripples in the energy of empty space, producing nothing and dissolving immediately back into the baseline. But in an eternal or near-eternal void, the improbable becomes inevitable. A new region of false vacuum nucleates somewhere in the infinite dark. Quantum inflation ignites. A new bubble of space-time expands at exponential speed, filled with a new set of physical constants drawn from the landscape of possibilities, populated by a new plasma of particles and radiation. A new universe is born, not from design, not from intention, from the same irreducible quantum restlessness that has been the engine of existence since before the word since had meaning. The same mechanism that produced everything we have ever known, producing something new, something we will never know, something that may never know us, something that may operate by laws so different from ours that the word law itself would be a mistranslation. And in that new universe, if the constants land right, if the fine-tuning lottery pays out again, as it must in a multiverse large enough and old enough, matter will organize. Stars will burn. Planets will form. And somewhere, perhaps, across billions of years of patient biological experimentation, a mind will open. It will look out at its cosmos. It will begin to measure. It will begin to ask. It will never know we existed, We will never know it exists. And yet, in some sense, that transcends the mechanical loneliness of that fact. We are connected. Not by signal, not by light, not by any force or field or quantum entanglement that spans the void between universes. We are connected by the question, by the act of wondering, by the fact that existence, given sufficient time and sufficient complexity, produces minds that turn back on existence and demand to understand it. That pattern, awareness interrogating the void that produced it, may be the deepest, most durable structure in the entire landscape of possible universes. Not a law of physics. Something more fundamental than a law of physics. A tendency, a pull, an orientation that reality seems to have, in at least some of its iterations, toward self-knowledge. The universe, perhaps, does not merely exist. It notices, and we are the instrument of that noticing. Fragile, temporary, made of recycled stellar ash, clinging to a rock in the outer arm of an unremarkable galaxy in one of 2 trillion, in an observable universe that is itself a vanishingly small region of an incomprehensibly larger whole, which is itself perhaps one bubble among an infinite foam of bubbles, each one a universe entire. And yet here, in this specific, improbable, fine-tuned pocket of everything, the cosmos opened its eyes through you. That is not a small thing. That is, in fact, the only thing, the only event in the entire history of the universe that changes the universe's relationship with itself. Not the formation of galaxies, not the ignition of stars, not even the synthesis of carbon in the cores of dying suns. Those are processes. Magnificent, necessary, beautiful processes. But processes nonetheless. Mechanisms running their course according to equations that do not require a witness. Consciousness requires a witness. Consciousness is the witness. And so when you look up at the night sky, when you find a dark enough place away from the light pollution of civilization and let your eyes adjust and see the Milky Way as a river of ancient light arching overhead, you are not merely observing the universe. You are the universe observing itself across 13.8 billion years of patient preparation. Every photon that reaches your retina has traveled for hundreds, thousands, millions of years to arrive at exactly this moment of contact between the cosmos and its own awareness. The universe has an end. What exists on the other side is silence and cold, and the long quantum patience of a void preparing to become something again. It is the death of every star and the evaporation of every black hole and the final dispersal of everything we have ever called real into a dark and featureless forever. And also, perhaps, the seed of the next everything. We are not the center of the universe. We never were. We are not its purpose. We may never know if it has one, but we are its most improbable achievement. The arrangement of atoms that learn to feel the weight of its own existence, to grieve the darkness at the edge of all things, and to find, in that grief, something that functions like wonder. The universe ends, and we were here to notice. That in the end may be enough.